All right, we are getting ready to talk about related rates. And it's a pretty complicated and challenging topic in AP Calculus. So today is just an introduction. And when we're doing related rates, it's important that we understand the chain rule and implicit differentiation. So the chain rule and implicit differentiation are important topics in finding the rates of change of two or more related variables that are changing with respected time. So the related variables and their rates are changing. So that's why we call it related rates. All right, so we're going to talk about some calculus language. And these are all things you've heard and written, but we're going to change them from words to symbols. All right, so if we have the rate that y changes with respect to x, that is going to be written as dy dx. All right, the rate that the area changes with respect to time. So most of the time, area is represented by capital A. That's going to be dA dt. That's the change in area with respect to time. All right, the next one takes it a step further. The volume is decreasing at a rate of 300 cubic meters per day. So volume is changing with respect to days, or volume is changing with respect to time. So that's going to be dV dt. Is means equals. Decreasing means negative. And then 300 cubic meters per day. All right. And then the last one, air is being added to a balloon at a rate of 45 cubic inches per minute. So air being added to a balloon is changing the volume. The volume is changing. So it's another dV dt. And if it's being added, it's positive. And then that's going to be 45 cubic inches per minute. All right. So we are going to need to be able to recognize that calculus language, write those types of equations like the last two to get through related rates. Today, though, we're mostly focusing on writing the initial equation, which relates a situation. Like these are going to be like volume formulas or area formulas or the Pythagorean theorem, and then using implicit differentiation to find the derivative. And then the next lesson, we'll start plugging in some values into it. All right, so for example 1, suppose x and y are functions of time, and x squared plus 2y cubed is equal to 5. We're going to find an equation that describes the relationship between the rate of change of x and y with respect to time. So that is a kind of a weird way to tell you, not really weird, but it's a way to tell you to find the derivative of that equation or that function with respect to time. All right. And so we're going to go ahead and use power rule. We're going to go ahead and use implicit differentiation. So we're going to find the derivative of x squared with respect to time. So we do the 2x power rule. But since we're not finding the derivative with respect to x, we have to multiply that by dx dt, right? Most all related rates are found with respect to time. And so if the variable you're using is not a time variable, it's not t, then you have to do that dx dt, dy dt, dv dt, something, all right? Then for the 2y cubed, we're going to do the power rule. And then since our variable is y instead of t, we're going to multiply that by dy dt. right? And then there is the rate of change of 5 doesn't change because 5 is a constant. So the derivative of 5 with respect to time is 0. Right? So that equation shows the relationship between the rate of change of x and y with respect to time. Right, these next ones, we are going to have to write the equation. So this one, the original equation, the relationship between x and y, not the rate of change. So anyway, I'll show you what I'm talking about on example 2. A rectangle is undergoing changes to its length and width over time. We're going to find an equation that relates how the perimeter of the rectangle is changing over time. All right, so let me draw a rectangle real quick. Now, oops, that's not very good. Drawing the picture is kind of important on related rates, I think. Okay, so here's my rectangle. So what's happening is the length and the width are changing. So an example to that would be like this. So the length is getting bigger, the width is getting bigger. This I don't have to both be getting bigger, but anyway, they're both changing. So because of that change, the perimeter is also changing. All right. So first, we're going to write an equation that just relates the length and the width to the perimeter. All right. So the things that are in this problem are length, width, and perimeter. So we need to know our perimeter formula. Now, if you guys come across a formula that you need to do your worksheet that you don't know, Google knows all the formulas. So just look it up. You can do it. All right, so that's the first step. We find an equation that relates the length and the width to the perimeter of a rectangle. Now we have to do what we did on example 1. We have to find the derivative of this with respect to time because we want to relate how the perimeter of the rectangle is changing over time. So we're going to find the derivative of p with respect to time. So that's just going to be 1 dp dt. All right. And then we want to find the derivative of 2L with respect to time. So that's going to be 2 dL dt. All right. And then for 2W, that's 2 dW dt. All right. That's the equation we're looking for. Okay. For example 3, a baseball diamond is a square with 90 feet on each side. A batter hits the ball along the third base line and runs to first base. We're going to find an equation that relates how fast the distance between the player and the ball is changing over time. So let me see if I can draw a baseball diamond real quick. Probably it's not going to be perfect, but maybe this program helps me draw straight, perfect lines. That's not too bad. It's not perfect though. But this is third base over here, and this is first base. So a player hits a ball down third baseline, so it's moving down for third baseline in this direction. So it's moving, and the player is running in this direction. So he's running, and the question is, how fast is the distance between the player and the ball changing? All right, so that makes a right triangle. So we have a special formula that we learned back in geometry that most everybody remembers that relates the sides of a right triangle to each other, and that's the Pythagorean theorem. I'm in the wrong place. Okay, and then in this situation, everything is changing. Like the ball is moving, the player's moving, the distance between them is moving. That's all changing. All right, so what I'm going to do is I'm going to find the derivative of this equation with respect to time. So we're doing the power rule, and since when I found the derivative of a squared, I'm finding with respect to time, so I do have to multiply by dA dt, right? And same thing on the b. And same thing on the C. So that's my equation that relates how fast the distance between the player and the ball is changing over time. All right, one last question, and this one is a little different. So water is flowing into a right circular cylinder with a radius of 2 inches. We're going to find the equation that relates how the volume of water is changing over time. Now, I put a note to be careful when one of the variables isn't varying. That has not been an issue so far, because on example 1, x and y were both varying. On example 2, the length and the width were both changing. On example 3, the ball was moving, the player was moving, the distance between was moving. Everything was varying. On this one, there is something that's not varying. So we have this cylinder. I'm going to try to draw. I'm not the best drawer. Okay. Now I know that the radius of this whole cylinder is 2 inches. And water is being poured into it, I think, flowing into it. So we have water. I'll make my water blue. It's flowing in. I'll draw. Right? And so let's think about that for a minute and think about what equation originally relates the volume of water inside a cylinder. And that's going to be the volume of the cylinder is V equals pi r squared H. All right, so as this water is getting poured in, there is one thing that is not changing. And that's either the volume is definitely changing because as water goes in, the volume is increasing. So between the radius and the height of the water while it's in the cylinder, try to think about which one of those is always the same. That's going to be the radius. So even as you pour more and more water into the cylinder, the height's going to change. The height of the water is going to change. The height of the cylinder doesn't, but the height of the water does. But the radius stays the same. So the radius is always 2 inches in this cylinder. All right, the radius of the water inside the cylinder will always be 2 inches. The height is going to change. So what I would do is put that R in. All right, so my equation that relates the volume of the water in the cylinder is V equals 4 pi H. Now what I want is an equation that relates how the volume of water is changing over time. So because I need that change, I'm going to find the derivative with respect to time. All right, now 4 pi is a constant that's being multiplied by the h. So whenever I find the derivative of 4 pi h, I'm going to multiply by that 4 pi. The derivative of h with respect to time is dh dt. All right, so be careful on that. While you guys are doing your work where you're writing your own equations, I gave you a hint on one where there is a part of the equation, there's a variable that doesn't vary in the situation. But I want you to think about it on all of them. Like when you write your equation, think like, are all of these variables changing or is one of them remaining constant? All right. Okay, so your assignment is to do topic 4.4 worksheet. Don't forget that I do have an office hours today, or Friday at 12 o'clock noon. If you have a question about this, you can hop on there. But we are going to jump into related rates on a higher level on Monday.